All right. Good morning, honors topics and physics students. I've already recorded this before, but I thought I was recording and I really wasn't, but that's okay. So what we want to do is talk a little bit about, we're starting the next unit on gravity, universal gravitation. And we want to talk a little bit about what went through his mind before or as he was developing the idea of universal gravitation. Um, so first off, Newton didn't quote unquote discover gravity. People had been falling to the ground for many, many years and dropping objects and seeing that they fell to the ground, that the earth attracted them or something was attracting them for many, many years. Newton didn't discover gravity. What he ended up discovering was that any two masses in the universe attract each other. Okay. So the story goes that Newton is sitting under an apple tree, and this apple falls off from the apple tree and bonks him on the head, and he starts thinking about it. He doesn't have a PlayStation and Xbox, so he's just kind of chilling and thinking. And Newton thought, well, the apple changed speed because initially it wasn't moving, then it started moving. Therefore, the apple accelerated, and since the apple accelerated, there must be a force on it. Okay, and what was causing that force? Starts thinking, bonk. Okay, and he starts thinking about the moon. So Newton knew that the moon's velocity was changing constantly. Okay, how is the moon's velocity changing? Is it speeding up and slowing down? No, but it's constantly changing direction. Therefore, it is accelerating. Okay, since it's accelerating, he knew that there had to be a force on it as well. Okay, and Newton thought, well, maybe the Earth, okay, pulled on the moon, just like the Earth pulled on the apple. Okay, could the Earth's gravity reach all the way out into outer space, out into the heavens? Okay, where would the Earth's gravity stop? Okay, and then he starts to think, well, if the moon is constantly being pulled to the Earth, why doesn't it fall and hit the Earth? Okay, bonk, like the apple. Okay, we're being attacked by the moon. Okay. Well, Newton realized that the moon and the apple are both falling just like projectiles, just like we learned about first semester. Okay, they're both falling towards the Earth. Okay, if we shoot a cannonball towards the Earth, okay, it's going to accelerate towards the Earth. If it's not moving fast enough, it'll fall and hit the Earth. Okay, if you shoot it a little bit faster, it'll go a little further. If you shoot it at just the right speed, okay, keep going faster. If you shoot it at just the right speed, it'll constantly fall towards the Earth, but it'll miss, okay, because it's moving too fast. It's moving at just the right speed to be in orbit. So, gravity pulls the moon towards the center of the Earth, providing the blank force to keep it moving in a circle. Does anybody remember what the force called that keeps an object moving in a circle is called? It starts with a C, centripetal. Centripetal force. Okay, so the Earth's gravity provides the centripetal force to keep the moon moving in a circular path around the Earth. Okay, but the tangential velocity of the moon is sufficient to keep it from falling into the Earth. Okay, remember that the velocity is always perpendicular to the centripetal force, which means it only causes it to turn. It doesn't cause it to speed up or slow down. Okay. Now, in order to get some backing behind his theory, okay, he wants to predict the acceleration of the moon and then see if it matches observation. Okay, so he knew that the apple on the Earth accelerates at 9.8 meters per second squared. But what would the moon do out in space? Well, the first thing he's got to consider is that the moon is a lot more massive than the apple. How is that going to impact the acceleration due to from the Earth? Well, if the moon and the apple were just above the surface of the Earth, which would hit the ground first, the massive moon or the tiny apple? We know that they would both hit the ground at the same time. So Newton knows he can ignore the mass of the moon because it doesn't end up matter. All things accelerate towards the surface of the Earth at the same rate, with a caveat from a given distance. Okay, okay, near the surface of the Earth. Okay, so heavy and light objects fall at the same rate, so he figured that the mass of the moon wouldn't affect its acceleration, so he can ignore that. But one thing he does have to consider is the fact that the moon is much further away from the center of the Earth than the apple. Okay, the apple is one Earth radius away from the mass of the Earth, the center of mass of the Earth. Okay, the moon is 60 Earth radii away, so it's 60 times as far away from the center of the Earth as the apple. Okay, so Newton reasoned that gravity would get weaker the further away you get. Okay, thinking of many things that do this. Magnets get weaker the further apart you pull them, and they would have experimented with these. Light gets weaker, sound gets weaker. So there's a lot of different models that would have led him to this conclusion. Okay, so he comes up with the idea that it should be 9.8 meters per second squared, the acceleration on the surface of the Earth, divided by the 60 squared, because it's 60 times as far. Okay, he uses experimentation with magnets and light and sound to come up with the idea that it would be 60 squared, not just divided by 60. And he realizes that the acceleration predicts the acceleration will be about 0.0027 meters per second squared, a lot slower than it is at the surface of the Earth. Okay, so on the surface of the Earth, if I were to shoot a cannonball or an apple out of a cannon, assuming it doesn't explode, okay, after 1 second of traveling, it will have fallen 4.9 meters below that gravity-free path. Okay. What about the moon with its much weaker acceleration? Okay, well, if I were to fire the moon out of a cannon, okay, it would have fallen 1.4 millimeters each second below that gravity-free path. So what he can do is use this model of how fast it would have traveled sideways and how fast it would have fallen and come up with the curvature or the radius of orbit. Okay, his answer matched what we know today, but he wasn't sure if the distance used should be the distance between the centers of the objects, and he didn't publish his results for another 20 years. Okay, even though he was right. Okay, but what would happen if the moon suddenly stopped? Okay. Moving along, managing its own business. Okay, what would happen? Well, the moon would fall towards the Earth. About how long do you think it'll take to hit the Earth if it stopped? How many hours? How many days? Okay, it would take about 3.5 hours for the moon to hit the Earth. Just a side note there. Okay, the Earth is orbiting the sun. What would happen if the Earth lost some of its tangential velocity? Okay, well it probably wouldn't fall into the sun. It would probably get closer and then speed up again. Due to conservation of rotational momentum. So the objects in our solar system have just the right speed to stay in orbit. If an object is moving too slow, it falls closer to the sun, and as it does, it speeds up and then regains a different orbital radius. Okay. Now, what makes and that's about actually where we're going to stop for today. Thanks for following along. Kind of a nice short day today. Enjoy the rest of your day.